Hello Roso buddies, we are currently in the month of February 2024. 2024 is the year where the month of February has 29 days. This is because the year 2024 is a leap year. And most of us know that a leap year happens every 4 years, but hold on a second. Are we really sure it happens every 4 years? To make sure about this, let's talk about the leap year. Welcome to Elmu Roso, with heart we care, with art we share. My name is Patrick, and I'll be your host. The leap year is a calendar year that contains an additional day compared to a common year. Why do we need this leap year, we ask? Well, let's start by talking about a year. A year is the time taken for astronomical objects to complete one orbit. A year on Earth is the time taken for Earth to revolve around the Sun. A year of Earth revolving around the Sun is equal to 365 days, 5 hours, 48 minutes, and 45 seconds. Or we can say 1 year is equal to 365 days, 5 hours, and 48.75 minutes. Or it is equal to 365 days and 5.81 to 5 hours, or equal to 365.24 to 1875 days. Looking at this decimal fraction number, we round it down to 365 days for 1 year by taking out the 0.24 to 1875 day every year. Hence, we get 1 year equals to 365 days. Next, let's use this leap year toolkit which has been made by our team, and let's select the leap year simulator. We see there are 2 circle objects showing on the screen. The big yellow circle represents the Sun, and the small blue circle represents the Earth. Now, let's enter year 4 and simulate the Earth revolution without any leap year and run the simulation. Now we see that the Earth is revolving around the Sun from year 1 up until year 4. Observe in the year 4 that the Earth has lost around 0.9 day, or almost lost 1 day. And if we continue to simulate the Earth's revolution without any leap year until year 20, the Earth has lost around 4.8 days, or almost lost 5 days. These happen because we took 0.24 to 1876 days from a year and rounded it down to 365 days for each year. To overcome this problem, we then add 1 day every 4 years, so that year becomes 366 days, and that 1 extra day is in the month of February. Therefore, in year 4, without leap year, we lost almost 1 day. With leap year in year 4, we almost rounded a perfect for revolutions, which only exceeding around 0.03 days. Without leap year up until year 8, we lost almost 2 days. And if we simulate up until year 8 with leap year, we almost return back to the starting position of the Earth's revolution, with an excess of around 0.06 days. Let's try to simulate until year 20. Without leap year, the Earth has lost almost 5 days, and if we simulate up until year 20 with leap year, the Earth has been adjusted almost to its starting position with an excess of around 0.15 days. Looking at this empirical data, while we were observing the simulation of the Earth revolving around the Sun and applying leap year, we found that the excess every leap year is increasing, although the increase is not that much when we run the simulation until year 20. But how about if we run the simulation until year 100 or even year 1000? Does this solution of adding 1 extra day every 4 years still solve the problem? Running the simulation until year 100 with adding 1 extra day every 4 years, the Earth exceeds around 0.78 days. And if we simulate until year 1000 with adding 1 extra day every 4 years, the excess is a whopping amount of around 7.8 days, almost exceeding 8 days. This solution of adding one extra day every 4 years seems not feasible to be applied for a long run. If we show the simulation with a graph, then the trend chart of the Earth's revolution without leap year will look like this. The total days decrease every year, while the trend chart of the Earth's revolution with adding one extra day every 4 years will look like this. The total days increase significantly every 4 years. The trend chart that we are aiming for is getting near to straight. So in October 1582, Pope Gregory XIII ordered the leap year rule as, every year that is exactly divisible by 4 is a leap year, except for years that are centurial years. Centurial years are years which have 0 tens and 0 ones in their place value numeration, like the year 100, 200 for 100. 1000, 1200, 1600, 1700, 1900, 2000, 2500. These centurial years are leap years if they are exactly divisible by 400. So the year 100 is not a leap year because it is not exactly divisible by 400. The year 200 is also not a leap year. The year 400 is a leap year because it is exactly divisible by 400. Same as the year 800 is a leap year, but the year 1000 is not a leap year, because again, it is not exactly divisible by 400. If we show the simulation with a graph, then the trend chart of the Earth revolution with the right rule of leap year will look like this. The line is jaggedy, trying to maintain the line to get near to an ideal straight line. The Leap Year Toolkit also provides a leap year calculator. With this calculator, we can check whether a year that we enter is a leap year or not. The calculator will show the result in an algorithmic way. Let's check year 4. Then click the first filter, then click the next one. We see that year 4 is exactly divisible by 4 with a result of 1, so year 4 is a leap year. Next we check year 7. The result is not a leap year. Year 100 is also not a leap year. Year 2000 is a leap year. Year 2024 is a leap year. The Leap Year Toolkit is accessible and we can download it for free at wirikara.ich.io/leap-year-toolkit. We've also put the download link in the video description. Okay, Roso buddies, that is all for now. And we'll see you back in the next episode.